Hello everyone, welcome to this presentation. In this talk, I will present the federated treatment of the Gaussian process and present the convergence results and also the application of the federated GP. My name is Xubo Yue. I'm a student from University of Michigan, Ann Arbor, and this work is jointly done with my advisor, Raed Kontar. A critical change is happening in today's computational framework. The computational power of edge devices is steadily increasing. For example, the Tesla autopilot system has 150 million times more compute power than the Apollo 11. Another example is that smartphones now have computational capacities comparable to laptops. Therefore, there's a new computing framework that exploits the edge compute resources to process more of the user's data where it is created. As a result, the modern era of computing is shifting from a centralized regime to a decentralized paradigm where the clients are collaboratively learning models while keeping their data stored locally. And this paradigm shift is often coined as a federated analytics. The idea of the FDA is very simple. It exploits the computational resources at the edge. The edge devices perform computations and only share the minimal amount of information needed to learn with the central server. As a result, FDA can preserve privacy, can reduce the storage costs, and also it's computational efficient. For more information about FDA, please refer to a recent published paper about the Internet of Federated Things. Now, let me formally present the FDA formulation. Let's suppose there's one global server, for example, the data processing center, and there are k local edge devices, for example, the automobile vehicles. The goal of FDA is to collaboratively solve the following objective function, where the PK is a weight coefficient for each device, and FK is a local loss function. The most fundamental algorithm to solve this objective function is called the federated averaging, or Fed average. Here I provide one simple example for the Fed average. At the beginning, the data center or the central server broadcasts a global model parameter to each device. The device then runs some local computations to generate a new model parameters, theta 1, theta 2, and theta 3, and send them back to the central server. The server will then aggregate all those parameters, for example, taking the weight average of those model parameters. Afterwards, the server will rebroadcast the global model parameter back to each device. And this whole process is known as a one communication round. And we will repeat this communication round for many times until convergence or some exit condition is met. Despite FDA has seen immense successes during the past few years, most FDA literature lies within empirical risk minimization framework, which is a direct consequence of the deep learning. More specifically, the loss function on each device K is defined as follows, which is in a summation form. Here, the LKI is a loss function evaluated at theta using the data point xk and yki. In other words, the loss function on the device K is separable and can be written as a summation form. To date, very few papers study FDA beyond this empirical risk minimization framework, especially when a correlation exists. In this paper, we go beyond the ERM framework and focus on the GP. Needless to say, the inherent capacity to encode correlation, quantify uncertainty, and incorporate flexible model prior has rendered GP a key inference tool in many applications, such as the multi-fidelity modeling. Therefore, the success of the FDA within Gaussian process may help pave the way for FDA to infiltrate many new applications and domains. To this end, we investigate both theoretically and empirically the possibility of federated model estimation in Gaussian processes, and also the applications where the federated Gaussian process can be of immense value. Now, let me first present some background on the Gaussian processes. Let's suppose the training data set is given as a d equal to xy, where the y is the output and x is the input. Here, n denotes the number of observations. We decompose the output y into the summation of fx and also epsilon x. Here, the f is a Gaussian process with mean 0 and also some prior recurrence function parameterized by the kernel parameter theta k. And epsilon is a ID noise that follow a normal distribution with 0 mean and sigma square variance. Now, given new observation x star, our goal is to predict the output, which is fx star. By definition, any finite collection of observations from a GP follows a multivariate normal distribution. Therefore, the joint distribution of the output y and the prediction fx star is given as follows, which is a normal distribution with 0 mean and this big coherence matrix. Here, this term k is defined as a coherence matrix whose entries are determined by the coherence function. Therefore, the posterior predicted distribution of the prediction is given as a normal distribution with the following identities. Based on these two predicted distributions, it can be seen that the coherence function k and the noise parameter sigma square are the most important components in the Gaussian process. Here, this coherence matrix k is determined by the aforementioned coherence function kernel, which is parameterized by the theta kernel. Therefore, predicting an accurate output fx star mainly depends on finding a good estimate of the theta, where theta contains the theta kernel and also the sigma square. To estimate the model parameter of Gaussian process, the most popular approach is to minimize the negative log conversion likelihood function or the loss function, which has the following form. As you can see, the key feature of the Gaussian process loss function is that this loss cannot be written as a summation form, which highlights the key difference between the optimization in GP and the empirical risk minimization framework. Therefore, optimization of the Gaussian process imposes a huge challenge, both empirically and theoretically. And I will provide more information later on. There are many optimizers that are readily available to minimize this loss function. In this paper, we will use a stochastic gradient descent to minimize this objective function. One question is why we want to use SGD rather than other optimizers. First, the SGD offers an excellent scalability solution to the computation complexity of the Gaussian process. From this loss function, as you can see, to optimize this loss function, one need to calculate the inverse of this coherence matrix, which is of n by n size, where n is the number of data points. As we have more and more data points, for example, the million of data points, inverting this matrix will cause a big O of n cubed complexity, which is very time consuming. SGD, on the other hand, take a subset of the batch data, and it overcomes the computational issue of optimizing the Gaussian process. Second, the SGD offers very good generalization power. A recent paper from Chen empirically validates that the solution obtained by the SGD generalize better than other deterministic optimizers. Therefore, SGD is a perfect candidate to optimize this loss function. First, let me talk about SGD of the Gaussian process in a centralized regime. Given a mini batch of size m, the stochastic gradient of the log likelihood function is given as follows, where the psi is a set of indices corresponding to a subset of training data, with a mini batch size M, and xi and yxi is a subset of input and output indexed by the xi. At each iteration t, a subset of training data is taken to update the model parameters as follows, where the eta t is learning rate at iteration t, and we will repeat this step several times until convergence. Now let me present the federated treatment of Gaussian process. Let's suppose there are k edge devices, and there's a central server that is connected to all the devices. For device k, the data set is given as a dk, which contains the input matrix xk and the output yk. And we assume there are nk observations on each device k. By lk, the local loss function for device k and also the gk is the stochastic gradient of this loss function with respect to a mini batch of data. In the FDA framework, our goal is to learn a global model parameter theta that minimize the global loss function, which is the weighted summation of the local loss function weighted by the pk. To fulfill this goal, during the each communication round, we'll use a Fed average to optimize this loss function. To be more specific, each local edge device k runs e steps of the SGD and updates the model parameter as follows. At the end of each communication round, the central server will aggregate the model parameter by taking the weight average. And this cycle is repeated several times until convergence. This algorithm briefly summarizes the federated Gaussian process. At the beginning of each communication round, we select the subset of devices by the sampling probability pk, and the server will broadcast the model parameter theta. After receiving the global model parameter, each local edge device will run some computation to update the model parameter using SGD. And afterwards, all the devices will send the parameter back to the central server. The server then aggregates those parameters by taking the average. And we will repeat this process for several times. For example, for our communication round. The natural question is why a single volume model works. Let's consider this example. Suppose we have two devices, and the true data generating function on device 1 is given as a y equal to x, and the truth for device 2 is given as a y equal to 3x. And ultimately, the averaging algorithm will return the global model, which is y equal to 2x. In this case, the global model does not fit into any device. Therefore, why the Fed average approach works for the Gaussian process? In fact, unlike the aforementioned example, the estimating model parameter theta in the Gaussian process is equivalent to learn a prior, so which predictions are obtained by conditioning on the observed data and the learned prior. And more specifically, in the Gaussian process regression, we impose a prior fk such that the fk will follow a Gaussian process. Therefore, learning a global model by the federated Gaussian process can be viewed as learning a common model pair over the fk. As you can see from the predictive equation at the testing location x star, the prediction of the Gaussian process depends both on this prior and also on the local data set. Therefore, the local data set on each device can be viewed as a personalized role in the Gaussian process regression. Therefore, the Fed average approach will work in the FDA framework. Here, let me provide some simple examples. Let's suppose device 1 has a data that follows y equal to sine x, while the device 2 has a data that follows y equal to negative sine x. And let's suppose each device has 100 training points uniformly spread within 0 and 10. We first use a fat average to train a two-layer neural network. And mathematically, we're solving the following objective function. By some algebra manipulation, it can be seen that the optimal solution is f theta equal to 0. We can also empirically validate this optimization problem. As you can see, if we train a network, you just return a straight line, which is f equal to 0, which means the fat average on the neural network or on the linear regression doesn't work in this case. However, as we mentioned before, the Federated Gaussian process regression will overcome this issue by learning common model pairs over the devices. While the final prediction of the Gaussian process will also depend on the local training data set. In this case, the fat average approach on the Gaussian process will work for both devices. After introducing the FGPR algorithm and also the advantage of our algorithm, our next step is to present the theoretical results of the FGPR. Here, note that proving the convergence results of FGPR is very challenging because the correlation exists also because of the decentralized nature of the model estimation. Remember that in the empirical risk minimization framework, the loss function for each device K can be written as a summation form, which means there's no correlation among data points. However, in the Gaussian process objective function, we cannot have this independent structure, and there's a correlation among all the data points. As a result, this correlation renders the stochastic gradient as a bias estimator of the full gradient. And this imposes a huge challenge on proving the convergence results of the Gaussian process. In fact, to the best of our knowledge, there's no similar work exists on this line. And our work is the first paper that proved convergence of the Federated Gaussian process when the correlation exists. Now let me present some setup for our theoretical results. We define the theta kernel as a theta 1 L, where such that the theta will equal to theta 1, theta 2, and L. Here, the theta 1 is a signal variance parameter in the Gaussian process, and the theta 2 is a noise parameter, and L is a length parameter. We will impose a structure on the Kranz function such that the Kranz function will equal to theta 1 squared times a kernel function. And this structure is very widely adopted. For example, the Mattern Kranz kernel or the RBF Kranz kernel. And we also have some assumptions on the Gaussian process. First, we assume the parameter space is compact and convex subset of the R squared. Without loss of generality, we assume the lower bound is theta min and the upper bound is theta max. And second, we assume the norm of stochastic gradient is bounded by a constant G. And we do not make other further assumptions such as the Lipschitz continuity or the bounded variance. And now, let me also present some assumptions on the kernel structure of the Gaussian process. The assumption 3A says that the eigenvalue of the kernel function K is exponentially decreasing. And this assumption is usually satisfied by the smooth kernel such as the RBF kernel. And another perpendicular assumption assumes that the eigenvalues of kernel function K is decayed in a polynomial fashion. And this assumption is usually satisfied by the kernel such as Mattern kernel, which is not smooth. And now let me present our results on the IED setting using the RBF kernel. By IED, we mean that the data distribution among all the devices are IED. Suppose assumption hold at each communication round. Assume all devices participate in the training. And under some mild conditions, we can prove that with a high probability, the model parameter will converge to the truth at a rate of 1 over t plus 1 plus some error terms. Here, the t equal to the number of communication rounds times the number of local steps e minus 1, which means the t is the total number of iterations indices on each device. And now let me analyze this convergence bound one by one. First, let's start from this red term. This term implies that with a high probability, the parameter iterator will converge to the global optimal solutions at a rate of 1 over t. Here, know that there's a term in this red bound, which can be written as e minus 1 squared over the t plus 1, where e is the number of local STT steps. In other words, to ensure that this term is decreasing with respect to t, we need to make sure the number of local steps e does not exist the square root of t, which means we cannot run too many steps on each local device. Otherwise, the FGPR will not converge. Second, let me analyze this blue term. In fact, this blue term is a statistical error that depends on the mini batch size. Theoretically, this implies that a large batch size is capable of reducing the error in the parameter estimations. Overall, as you can see, our convergence results depends both on the total number of iterations t and also on the statistical errors. Similarly, we can prove the convergence results for the partial device participation scenario where at each communication round, only a subset of devices are selected. Also, we can prove the convergence of FGPR using the Matrix kernels. And for more information, please refer to our paper about those theoretical results. And next, let me present the convergence results on the non-IED scenario, which means the data distribution among all the devices are not IED. And this is a more realistic situation in many real-world applications, because in many applications, we cannot ensure the data are IED among all the devices. Now let's suppose a aforementioned assumption hold. At each communication round, we also assume all devices are selected. Then under some mild conditions with high probability, the norm of the gradient of full likelihood is upper bounded by this term. As you can see in these results, the first part is also bounded by the big O1 over t, which means as we run more iterations, this term will decrease very fast and go to 0 as t goes to infinity. Additionally, we also have the statistical error that depends on the mini batch size mk, which means a large mini batch size will decrease the error in the estimations. And also similar results hold for the partial device participation scenario and also for the Matrix kernels. Due to time limitation, I will skip all those results, and please refer to our paper for more information. Now let me present some simulations to validate our theoretical findings. We will only validate our theoretical results on the homogeneous setting, where the underlying process to generate data among all the devices are IED. We first generate data from a Gaussian process with RBF kernel or with a Matrix kernel. And we assume there are k devices in total, and each device has nk number of data points. We also define the big N as a summation of nk. To ensure a homogeneous distribution among the devices, we assume the underlying truths of the model parameters are same among all the devices. To ensure a balanced distribution of the data, we assume nk are equal among all the devices. We train FGPR on the k devices and obtain the final estimated global model parameters. In this figure, we plot the difference between the estimated model parameter and the global optimal model parameters with respect to the communication route. As you can see, all the patterns follow the big O1/T trend, which means our theoretical results is correct. From this figure, as you can see, there are some fluctuations during the convergence. This is because on each device, we only have around 8 number of data points. Remember that the convergence results is also affected by the mini batch size M. If the M is too small, you can see there's some statistical error in the convergence bound. And also the convergence speed is slightly affected by the small batch size. And a similar results will hold for the RBF kernel. And next, let me present a setting with the homogeneous data and also the unbalanced data. By unbalanced distribution, I mean on each device, we have a different sample size. And this histogram plot the distribution of the sample size for all the edge devices. Again, from this plot, we can see that the estimated global model parameter will converge the true parameter at a rate of big O1/T. This further validates our theoretical results on the homogeneous setting. And finally, let me present one real-world study based on the multi-fidelity modeling. For many computer experiments, the high-fidelity simulations of a very complicated physical process typically require a significant amount of budget and time. And this limits the number of data points researchers can collect. And this also affects the model accuracy due to the insufficient amount of data. A major trend work has been proposed to augment the expensive data source with a cheaper surrogate to overcome this difficulty. A multi-fidelity model are designed to fuse the scant but accurate observations, i.e. the high-fidelity model, with a cheap and biased approximation, or we say the low fidelity, to improve the high-fidelity model performance. Denoted by FH, the high-fidelity function, and FL, the low-fidelity function. The goal of the multi-fidelity model aims to use the FL to better predict the FH. Among all state-of-the-art models, the Gaussian process-based approaches have caught attention in this area due to its ability to incorporate prior beliefs, interpolate complex functional patterns, and also quantify uncertainties. And the ability to quantify uncertainty is critical to fuse observations across different fidelity effectively. To be more specific, the Gaussian process-based approaches model the high-fidelity function as below, where this rho is a space-dependent nonlinear transformation of the low-fidelity function and also the input x. And this delta x is a bias term modeled through a Gaussian process. And there are several approaches to solve this Gaussian process model. For example, the autoregressive Gaussian process model this term as a linear product between the constant rho and also the low fidelity function. And the deep Gaussian process will use a more complicated things, where it models this rho function as a deep neural network using the Gaussian process. Nowadays, as this privacy gains increased importance, having access to data across multiple fidelities is often practical, as different devices can own their own data. For example, the high-fidelity devices cannot share the data with the low-fidelity device, and vice versa. This imposes a key challenge in the multi-fidelity modeling approaches, as the high-fidelity models need to use and borrow the strengths from other information sources. Fortunately, in this case, FGPR is a potential candidate that learns the Gaussian process prior without sharing the different fidelities of data. In this setting, we assume each device has one level of data fidelity, and our goal is to improve the high-fidelity model predictions. During the training process, devices only share their model parameters with a central orchestrator without sharing the data with each other. Here, let me provide two simple examples. Let's suppose on device 1, we have low fidelity data, which is defined as follow. And for device 2, we have high fidelity data, which is defined as follow. Here, YL is the output from low fidelity model, and YH is the output from the high fidelity model. We simulate 100 points from the low fidelity model and 20 points from the high fidelity model. The number of testing data points for the device 1 is 1000. In example 2, we create a nonlinear example which has a following structure, and we use the same data generating strategy as example 1. This plot presents the results for the multi-fidelity modeling for example 1, example 2. And here it's a data fit for the example 1 with the low fidelity model, and second one is a model fit for the high fidelity model. As you can see, the learned FGPR is able to accurately predict the high fidelity model, despite we have very few observations. And similar conclusion holds for the example 2. This further demonstrates the importance of borrowing strengths from other devices using the idea of the FDA. Additionally, we can see that the FGPR can accurately capture the uncertainties in the predictions, where the confidence interval is presented in the gray color in those plots. This also demonstrates the advantage of the FGPR in quantifying uncertainty in predictions. Now, we also consider several more complicated data sets. For example, the current dataset and the borehole dataset. For detailed information for the setup of this dataset, please refer to our paper for more information. We compare the FGPR with several state-of-the-art multi-fidelity modeling approach, such as the autoregressive model and the deep Gaussian process model. Here, note that because the AR benchmark and the deep benchmark cannot be applied to the federated setting because they need to share the data with each other. Therefore, in those benchmark model, we will assume the different fidelity can share the data with each other. However, in our setting, the device will not share the data with the central server. As you can see, despite the benchmark model use the data across multiple fidelities, it still yields a inferior performance than our FGPR framework. This further demonstrates the advantage of FGPR in the multi-fidelity modeling. And we also argue that FGPR can be a potential candidate for the multi-fidelity modeling approach. In this paper, we extend the standard Gaussian process regression to an FDA scenario, which we call the FGPR. We use both theory and a wide range of experiments to justify the viability of FGPR in the real-world applications. That's all for today's presentation. Please let me know if you have further questions.